Greetings and welcome. My name is Annette Vegas. The topic for discussion today is the physics of ultrasound artifacts. This session will explore the topic of 2D ultrasound artifacts. Hopefully, by the end of this session, you will be able to identify common 2D ultrasound artifacts, understand the physics behind 2D artifacts. We have a lot to cover in a short time, so let's get started. Artifacts, by definition, are any error in imaging. Artifacts are important to recognize for the reasons listed here. The object may not be real, resulting in a wrong diagnosis. The object may be missing, resulting in real findings being missed. The object may be an incorrect size or place, resulting in wrong measurements. The cause of an artifact may be from equipment malfunction, operator error, lack of understanding of ultrasound physics, or a violation of sound assumption. Let us begin with familiar territory by reviewing the sound assumptions made with ultrasound imaging. Sound travels in a straight line at a constant speed and directly to the reflector and back. The imaging plane is thin and only reflections from the main beam axis are displayed. Reflections are related to tissue characteristics. Not all these assumptions hold true, so when they are violated, artifacts will form. It is often difficult to understand artifacts because they involve understanding physics, are hard to categorize, or described by different terms. For the sake of this presentation, we will use the following classification for artifacts based on physics principles. Propagation artifacts relate to the sound wave and include reverberation, refraction, multipath, grating lobe, and range ambiguity. Attenuation artifacts relate to medium interaction and include acoustic shadow, enhancement, and focal enhancement. Resolution artifacts relate to returning echoes, and these include those listed here. This covers most of the ultrasound artifacts. We will simplify things by considering the following: representation of the transducer, sound beam, sound wave that is sent and received, the medium, and cardiac structure. The first set of artifacts relate to problems with propagation path and include the following main groups: reverberation or bouncing of the ultrasound signal, including mirror image, comet tail, and ring down. Refraction or shifting of the ultrasound signal, as in ghosting, speed error, and edge shadowing. Side or grating lobes and range ambiguity are two other artifacts. Reverberation artifacts involve the bouncing of the ultrasound beam between two reflectors that involve either big or small structures or air. These artifacts appear as echoes of an echo, as single or multiple artifacts. They are equally spaced lines of decreasing amplitude, parallel to the sound beam, and deeper to the structure along a straight line. A mirror image artifact is a type of reverberation artifact. and results from returning sound bouncing from a strong reflector, in this case the aortic wall, back towards the aorta, and then onwards to the transducer. This produces a less intense second image, deeper at twice the distance to the structure. The same structure occurs in more than one place. This artifact may also occur with color Doppler. Common examples include the upper esophageal aortic arch long axis and descending aorta views. To understand the physics, normally the ultrasound machine assumes that the returning echo occurs from a single reflection with the object depth relating to the time for this round trip. In this case, the returning echo repeatedly reflects back and forth between two parallel, highly reflective surfaces before returning to the transducer. The ultrasound processor sees sequential echoes taking longer to return to the transducer and erroneously places the delayed echoes at a greater distance from the transducer. A comet tail artifact is a type of reverberation artifact. In this case, a small reflector repeatedly reflects returning sound in line with the ultrasound beam that appears as a single strong linear echo deeper than the reflector. The sequential echoes may be discrete, clean shadows, or so closely together that the individual signals are indistinguishable. The echoes have smaller amplitude and appear with a decreased width or as a tapered triangle. A ring-down artifact is often confused with a comet tail artifact and thought to be a reverberation artifact, but it is not. The artifact results from continuous resonance of fluid trapped by air bubbles. An alternative explanation is that small, weak reflectors allow some echo transmission. This produces multiple reflections that appear as numerous thin, closely spaced lines that are less discrete, adding streaks to create a dirty shadow. Refraction is the bending of transmitted and reflected waves. The sound wave changes direction when A. it strikes a boundary obliquely, or B. the media have different propagation speeds. Ultrasound beam reflects off structures outside of beam planes and results in artifacts such as ghosting, speed error, and edge shadowing. Question 4. What artifact is shown in this midesophageal aortic valve long axis view to account for the overall image degradation? This is an example of ghosting. A ghosting artifact represents a refraction type artifact with sound striking a curved boundary obliquely. Sound changes direction, or bends, when it passes obliquely through an interface between two substances that transmit sounds at different speeds. The degree of directional change is governed by Snell's law, according to the incident angle of the ultrasound beam and the difference in velocity between the two media. Echoes return from a structure located along a different path than that of the returning beam. A structure appears anatomically lateral to the returning beam path and is interpreted by the machine as located in the path of the returning beam. A refraction artifact may cause structures to appear wider than they actually are, or are a duplication of structures. This creates extra echoes as a second copy of the true reflector appears side by side of the true anatomic structure. The objects appear in different positions than they actually are. This degrades lateral resolution as the edges appear blurred. An edge shadowing artifact is a type of refraction artifact and is not a result of acoustic shadowing. The ultrasound beam bends at a curved structure, losing intensity, to produce a shadow that appears as small dark areas, anechoic, under the edges of a circular structure. Sound traveling from a higher velocity to a lower velocity medium will give a narrow shadow. A wider shadow forms when sound travels from a lower to a higher velocity region. To understand the physics, when sound waves encounter a curved surface at a tangential angle, they are scattered and refracted. The result is a lack of echoes from anything in a direct path posterior to it. This has an appearance of a linear shadow. This artifact may disappear when changing the angle of the ultrasound beam clarifies the nature of the artifact. A grating lobe artifact occurs using a phased array transducer. It is referred to as a side lobe artifact if a single array probe is used. The ultrasound beam signal transmits along the main beam, but may have off-axis beams as well. These lobes reflect off highly reflective structures, creating multiple structures on either side, which appear as a curved arc at the same level of the true object. These artifacts appear hyperechoic, superimposed over structures from improper off-axis locations in the image. To understand the physics, every transducer has a main beam, which transmits parallel to the transducer long axis. Linear array transducers also have multiple low amplitude beams that project radially at different angles away from the main beam axis. The machine cannot differentiate between reflected beams returning from the main beam or those from off-axis lobes and considers any detected beam as coming from the main axis. Side and grating lobes have a lower amplitude, so for transducer detection, they must reflect off highly echogenic structures. Grating lobe artifacts appear as a hyperechoic object within an anechoic or hypoechoic structure. Question 7. What artifact appears in the left atrium in this midesophageal four-chamber view? This is an example of a range ambiguity artifact. A range ambiguity artifact is a type of propagation path error. In this artifact, the pulse sound returns late after the second pulse is sent. There is a late reflection from a reflector beyond the scan area. Thus, echoes from the deeper structures appear closer than their actual location, and as an unexpected intracardiac echo. To eliminate the artifact, change the depth or probe position. To understand the physics, the ultrasound system assumes that all received echoes are from the most recent transmitted pulse. Ultrasound pulses are sent intermittently between silent periods awaiting returning echo signals. Returning echoes are assigned a depth based on the time interval between the transmitted pulse and the detected echo. A returning echo from a reflector beyond the scan area returns late, making the deeper structures appear closer than their actual location, and as an unexpected intracardiac echo. Attenuation is most often associated with loss of sound beam energy, though in some instances less energy is lost. Attenuation artifacts include acoustic shadowing, enhancement, and focal enhancement. An acoustic shadowing artifact is an attenuation type artifact. There is loss of ultrasound beam transmission from high reflection or absorption involving a high density structure, such as calcium or prosthetic valves. Distal structures are not seen, or anechoic, or appear as a gray shadow. This shadow shape follows the ultrasound beam path, such that a small structure close to the transducer casts a long shadow. To understand the physics, when the ultrasound beam encounters a tissue that attenuates sound to a greater extent than the surrounding tissue, the beam strength distal to the structure is weaker. The echoes returning from the structures beyond the highly attenuating structure is diminished. The hypoechoic or anechoic band occurring deep to a highly attenuating structure is called shadowing. Question. Question 9. What artifact is the blue arrow pointing to in this transgastric? An edge enhancement artifact is a type of attenuation artifact. The proximal structure has low sound absorption, which allows more sound transmission, making the distal structure reflect more energy. Thus, distal structures appear brighter, hyperechoic, under tissue of low attenuation that are hypoechoic. This is the opposite of shadowing. To understand the physics, as sound passes through solid tissues, it is gradually attenuated. Fluid-containing structures attenuate sound much less than solid structures. There is an increased transmission of sound that produce stronger reflections, which appear brighter than identical interfaces deeper to solid tissues. Mid-short axis. A focal enhancement artifact is a type of attenuation artifact. The artifact occurs around the focal zone and appears as an increased side-by-side intensity or extra echoes. There is too much band brightness compared to the depth, which is the same appearance as incorrect TGC or time gain compensation settings. To understand the physics, the focusing characteristics of the transducer creates a banding artifact, which is a band of increased brightness caused by greater intensity, usually in the focal zone. This is more noticeable with systems with fixed transmit focusing and dynamic receive focusing. This group of artifacts relates to image quality and includes problems with axial resolution, lateral resolution, elevational resolution, dropout, speckle noise, and near-field clutter. The main ultrasound beam has thickness as it exits the transducer, which can create an artifact. As the beam propagates away from the transducer, it narrows gradually until it reaches the focal zone and then gradually widens. Structures proximal to and distal from the focal zone are prone to artifacts, resulting from volume averaging between adjacent objects within the thickness of the beam. In other words, the thicker the image slice, the more likely that two different adjacent objects will fall within the image slice. Minimize this artifact by placing the focal zone at the level of the structure of interest. This is a dropout artifact, which is a type of resolution artifact. In everyday imaging, we perhaps do not recognize this as an artifact, as it appears as a normal part of the image. Nevertheless, this is a dropout artifact on the septal and lateral walls of the LV. This artifact is commonly attributable to signal attenuation from inadequate brightness or power. To understand the physics, in this case, the artifact arises from the result of the imaging beam being parallel to the structure. This is the concept of anisotropy, in that some structures have properties that differ according to the direction of inclination. When the transducer angle changes by as little as 5 degrees and is not perpendicular to the structure, there are fewer returning echoes, which results in a hypoechoic area. You can see this goes away when the ultrasound beam is perpendicular to the structure. Question 11. Question This is an example of acoustic speckle in which there is interference of returning scattered sound waves reflected from tissues. These small amplitude echoes make the image appear grainy. Image quality improves with harmonic imaging. Tissue harmonic images are obtained by collecting harmonic signals that are tissue generated and filtering out the fundamental echo signals that are transducer generated, resulting in crisper images. High amplitude oscillations of piezoelectric elements create extra echoes in the near field, making it difficult to differentiate near field structures. This is common with an epiaortic probe and can be reduced by using a standoff with a saline-filled glove. In TEE and TTE, this can be eliminated by using harmonics or adjusting the near field gain. So in summary, artifacts are common. Learn to recognize them. Don't misdiagnose, and make pretty pictures. Question 13. These are some useful references for this topic. 13. Thank you very much. What artifact is the blue arrows pointing to in this epiaortic descending aorta short axis view? The correct answer is near field clutter. Question 12. What ultrasound machine knob was adjusted to eliminate the artifact the blue arrow is pointing to in this mid-esophageal aortic valve long axis view? The correct answer is harmonics. What artifact is the blue arrows pointing to in this transgastric mid-short axis view? Why does it appear so dark? The correct answer is this is the dropout artifact. Question 10. What artifact is the blue arrow pointing to in this transgastric mid-short axis view? Why does it appear so bright? The correct answer is focal enhancement. view. Why does the pericardium appear so bright? The correct answer is an enhancement artifact. Question 8. What artifact is the blue arrow pointing to in this midesophageal view of a mechanical bileaflet mitral valve? This is a shadowing artifact. Question 6. What artifact is the blue arrows pointing to in this midesophageal aortic valve long axis view and modified four-chamber view? This is a grating lobe artifact, as a phased array transducer is being used. Question 5. What artifact is the blue arrows pointing to in this midesophageal ascending aorta short axis view? This is an example of an edge shadowing artifact. Question 3. What artifact is the blue arrow pointing to in this modified midesophageal aortic valve long axis view? This is a ring down artifact. Question 2. What artifact is the blue arrow pointing to in this routine midesophageal descending aorta short axis view and midesophageal view of a mechanical mitral valve? The correct answer is 4, a comet tail artifact. Question 1. What artifact is the blue arrow pointing to in this routine midesophageal descending aorta long axis and short axis views with and without color? The correct answer is 3. This is a mirror image artifact, a type of reverberation artifact.